surprisingly.
I'm getting the recording started here. Yeah, we were just talking about this TASI workshop on what, black hole thermodynamics and string theory.
Yeah, quantum information and
cool.
duality.
That's
Yeah,
pretty cool.
but
yeah, sounds good. But that conflicts with this time, though, right?
yeah, for the month of June, it would be I'm free after 5, but there may also be, I don't know if there's going to be stuff after the lectures. So yeah, I don't, you know, they're like, oh, the watch a movie and eat dinner, or I don't know.
Yeah, is this all Zoomed, or how is it done, or is it?
Yeah, it's Zoomed this year.
Okay. Yeah.
So yeah, that would just be one thing in the future.
Yeah. How long does that run?
It's a month. It'll be the 7th to the 2nd. So
yeah, okay, full month. All right. So we may have to. It might be best to just shift the day.
Or if you guys, or I could watch lectures and type in questions.
Yeah. Okay.
After the fact, I can try to.
Yeah. So
like catch up if I'm really lost.
I mean, I don't mind. It doesn't bother me if we move the day. So
yeah.
Yeah. You know, from my perspective, the days look pretty much the same. So yeah, I'm fine with that. So let's try this and see how it goes. But we can shift. Now let's see. We're still missing a couple of people. Yeah, I hope they haven't forgotten. But let's start. We're recording this so they can check that. And I want to back up a little bit, because that last the final basically was a bit rushed, right? So I wanted you guys to be able to actually do a QED calculation, but we let's see, we got the rules for quantum electrodynamics. I sort of raced through the derivation. So why don't we start with chapter 10, QED. And, you know, if you're looking bored, we can hasten through some things, but I think it's probably worthwhile spending a little more time on a few of the calculations there, what underlies the QED Feynman rules and how we use them. So going back, let's see, we have the Dirac Propagator, which is actually pretty easy to get, right? Let me get a marker here and just re-enter the sense of actually giving lectures and writing on the board and that sort of thing. It was, it's been a pretty wild few weeks. So, let's see.
Has it been wild? Have you been up to some wild stuff? Just general post semester.
Yeah, you know, there's been a lot going on. You know, both, well, getting grades in for the courses and all that, but also, we refinanced our house. You know, it's amazing. We could do almost everything online. So all the paperwork was done inside of a day, which was pretty amazing. And I don't know, just the first chance to get chores done around home or in town, that kind of thing. Meg and I are getting back to bicycling. We try to bicycle most every day, so we've been doing that most days. I don't know what else. It just seems like a lot of little things that we took care of. Yeah, we shipped our old car off to Michigan. You know, we got another car, and I gave my brother the old one. We had a Mazda van that we've had for 15 years, and he'll really appreciate. So that's in Michigan now. You know, just, I don't know, lots of little things like that. So
yeah, shipping a car is a little thing for sure.
yeah,
Oh my gosh,
right. Well,
it's awesome.
it took a little time. You got to, get the title signed and, just all the little things involved in transferring a car mostly. And, insurance, those things. But the Dirac equation, right? Here we go. So we've got I u slash minus m psi. All right, so there's the Dirac equation. The equation for the propagator or the green function, however we might want to call it, is this. So we're going to put an I del 4 of x minus x prime over here, and that's let me use x minus y here. Okay, good news. I got a whole new box of blue markers, so we won't run out of functioning markers. So we do the same thing. We're interested in the momentum space representation for all this. That's where all the Feynman stuff happens. So we write each of these things as in terms of the Fourier transform, but there's a bit of a subtlety to G, which really comes out in the wash. Remember that this is an operator in two spaces. It's a differential operator in space-time, and it's a matrix operator in the four-dimensional complex space. So G is going to have a dual character, and we'll see what that is. Now, on this side, there's actually an identity matrix in that complex space. Can you folks see the board okay? Is this showing up all right?
Yeah, I can see it just fine.
Okay, all right, good. So, I'm gonna just double check. Yeah, pull up the participants page just in case someone comes in. I want to be sure I see them. Okay, so Fourier transforms. We're going to write G as the integral, and let's see, d4k by 2 pi to the 4th. And these factors of 2 pi, there are conventions in the Fourier world. Which have sort of changed. E to the minus I, k dot x minus y here. And then the delta is basically the same thing without an integrand. So 2 pi to the 4th here. Yeah, so one might use 2 pi squared here for a four-dimensional integral, but then here there's no integrand. It's just k dot x minus y. And when we substitute this in, this is going to give, all right, we have ID slash, so this is going to pull down a k. So we're going to end up with the integral d4k over 2 pi to whatever power you prefer here. Then substituting in G, the x dependence is going to pull down a minus ik. So we're going to have I with a minus ik slash, because this is contracted with a gamma, minus m, acting on G tilde. And then on this side, this is going to give just 1 times the exponential. So if I bring this to the other side, we get a minus I here, and then the Fourier exponential. Now, this is now the Fourier transform of this equation. We can take the inverse Fourier transform, and it means that this integrand vanishes. So what we have is now, let's see if we cancel an I. Let me be sure I'm getting this right. ID slash Yeah, this is on that. So this goes away. So we get K slash minus M acting on G equals I. And we don't often write the 1 there, but there's a 1 there. Okay, so how do we solve this for G? Because this is still a matrix equation. And what we can do is multiply by something that simplifies this. If we multiply by K slash plus M, K slash minus M, G tilde is now K slash plus M. And this, I'll work backwards here. All right, what's K slash squared? Now this comes up a lot. Gamma mu, gamma nu. All right, we've got to keep the gamma matrices in order. You've done a fair amount of this with the final multiplying and reducing these gamma matrices. But let's just say what happens so that it's totally clear how we handle it. The point is, this is symmetric in mu nu. So I can write this as K mu, K nu with a half, and I can symmetrize this, gamma mu, gamma nu, plus gamma nu, gamma mu. And that's the anti-commutator, so it's equal to twice the metric. So this is K mu, K nu, times a half times twice eta mu nu, times the identity matrix, if we're putting in everything. And the twos cancel, of course, and we just get K squared. So we just get K squared with an identity, and the identity multiplied by the G just gives G. So all of this just becomes K squared minus M squared times G tilde. And now this is just a function. This is just some number for each K. And so we can write G tilde as K slash plus M over K squared minus M. And recall our offsetting of the poles in the complex plane. So you could have a plus I epsilon here to offset those poles if we were going to integrate back to find the space-time form of the green function. So this is the Dirac propagator. It's important to notice the plus sign in the numerator because we've inverted the minus sign. So the only other thing is, oh, there's an I. I lost this I. There's still an I here. So we have an I, and this is often written as I over K slash minus M, just as a shorter way of writing what we know is really the same thing. Now, 1 over a matrix is a weird thing to write, but we know what that means. It means this other thing, this matrix times some function. Okay, so there's our propagator for the Dirac field. Then I went through this calculation again, and it it felt a lot better the next time through doing it again. Yeah, remember for the scalar field, for the scalar field, we did these manipulations where we integrated and differentiated by time, and then we used the field equation and some integrations by parts to get the prefactors in that matrix element. And it's far from clear that that all actually works for a Dirac field as well. You know, we had second derivatives in time, and we used the D'Alembert-ian, and it was responsible for the cancellations of the K squared minus M squared factor on the external lines. So when we actually analyzed some Feynman diagrams for the scalar field, the propagators gave us these factors of 1 over k squared minus m squared. And those canceled with prefactors of k squared minus m squared when the wave operator, the Klein-Gordon wave operator, acted on the asymptotic fields, the asymptotic free fields. So to see that that still happens in the Dirac case, I went through it again, and it still works. Do you guys want to see it? Or did you work through it? Let's see, I'm not hearing you.
Is it in the chapter?
It's in the chapter. So you worked through it. Did you work through that, Eli? Or do you want to see that? It's, you know, it's about a page of calculation where you insert, let's see, you've got the Fourier transform of the mode amplitudes, basically.
Right.
And you insert a time derivative to make it a 4-dimensional integral. And everything goes through. Right, you end up with basically 1 over the propagator that will cancel when the wave operator acts on the free field. So I'll let you guys read that if you haven't already. If you have any questions on it, we can come back to it. Then I redid the quantization of the photon. Now, let's see, we talked quickly through that, right? And the technique is to look at basically a bigger class of theories that have an additional parameter. So you actually change the action. You put in a divergence of a term. So here's what that looks like. And this allows us to use a simpler propagator. Actually, it means we have a non-degenerate propagator for something akin to the vector potential. And then we worry about the gauge condition later. So we take this, the action, the space-time integral of -1/4 f squared, where f is the usual curl of a vector field. But now it's an ordinary vector field because we add a term d mu, a mu squared. And that means that we no longer have gauge invariance, right? F is invariant if I change A by a gradient, but d mu A is not. You get, if I added a gradient to A, you get the D'Alembert of that function, whatever function you were adding the gradient of. So this action is no longer gauge invariant. And as a result, the conjugate momentum for the vector field doesn't vanish. So we don't have that, that projection operator in the problem the way we did before. If we calculate the conjugate momentum, all right, that's varying the Lagrangian with respect to A0 dot, it turns out that that is -1 over psi d mu a mu. So this is this factor that saves us. If you take that to 0, if you take 1 over psi, if you take psi to infinity, this term is 0, and you return to Maxwell theory, and this vanishes. But what we'll see is that the extra degrees of freedom that this introduces don't actually contribute to observable quantities. So the quantization procedure is straightforward canonical quantization. let's see, I work through it and we find that we can write the same steps as usual, and we get A is now a 3k over some normalization here. What did I use? 2 pi squared. Okay, so now I'm back to the old normalization for Fourier integrals. And then we have Fourier modes, a mu of k minus I k dot x plus a mu, if it's a real field, that's going to be the conjugate e to the I k dot x, where then I've already integrated over a delta function. So omega here is omega of k, satisfying the wave equation. The equation of motion for A has additional terms. So it's not just the usual gauge thing. Maxwell theory gives you something like this, where you have the alpha d mu, a mu. It gives terms like this, but now this term is going to have something like a psi contribution. Oh, yeah, it's exactly that. With this probably minus this and plus that, but the wave equation contains a D'Alembert, but then you have a factor multiplying the gradient of the divergence. And this term would be removable in electromagnetism. You could use the gauge freedom to get rid of that term, but here you don't. You can let psi be anything you like. Yeah, in fact, yeah, there's a choice, probably wrongly attributed to Feynman, but it's called the Feynman gauge, where that psi is taken to be 0. I think. Is that right? Let me go on down a little bit here and see where psi comes in. The next calculation is the somewhat lengthy inversion of the Fourier series. So what we want to do is to introduce polarization vectors. So these, as a result of this field equation, these A's satisfy some condition, all right? And depending on the value of psi, you get different conditions. But what I want to do is put those conditions onto the polarizations as much as I can. So I'm gonna put in another root 2 pi to get this normalization right, and then I want a polarization vector, real or complex, and then all right. So we have several polarization vectors, and for each of those, we're going to have some amplitude. So for each lambda, there's some amplitude A of k. So with that substitution, we've separated the polarization vectors from the wave amplitudes. And then we can solve for the wave amplitudes. And when we quantize the fields canonically, it will imply commutation relations for those wave amplitudes. A, and this becomes an A dagger when it's an operator. Now, the condition we impose on these polarization vectors is if we sum over all of them, got a visitor here, epsilon lambda beta. If we sum this over all lambda, we want to get 1 if we're talking about the spatial polarizations. Remember, we want our ultimate theory to describe a transverse electromagnetic wave. And so we take this to be minus eta alpha beta, so that the spatial ones are positive 1. Let's see. Oh, looks like that's wrong in the notes. It's right later in the notes. I'll have to go back and correct that. Now, we've got a visitor. Rubbing against my legs. Say hi, Rosalind. Yes, hi. There we go. All right. So rather than write pages of inverting Fourier transforms, you can find that in the notes, and I can go right to the results. Let's see. So the Fourier transform of A mu and pi mu is a linear combination of the A and A conjugate fields. The only thing that's really different about this is that the conjugate momentum for A0 is actually a divergence of A, which means it depends on all 4 of the components of the vector potential. That doesn't really cause any problem. You just carefully carry it through. So you find the Fourier transform of the first 3, the spatial ones, first, and then you can substitute that in along with the A0, and you get a solution. So by the time you boil through all that, and you know, it takes a couple of pages, but you get something that looks like A mu minus I over omega pi mu, or in the case of A0, it's A0 minus I over omega n dot pi, where n is a unit null vector. Oh, this cat is in heaven. Yeah, I don't know. She's suddenly taken up a liking for quantum field theory. Who knew? Who knew? Yeah, she. This is her daily neck massage. Okay, so now go on. I might need my hands here. All right, so yeah, the result for that is top of page 244. It's the usual thing. It's the Fourier transform for the 4 different polarizations. We get a Fourier transform of basically A minus I over omega times pi stuff. The forms are nicely parallel there. So now canonical quantization, and we can take a mu hat with pi mu hat to be covariant, right? We can have now I h bar is 1 eta mu nu, then a delta function. Or let's see, this is these are going to be functions of p and k, right? Or well, no, they start out x minus y. So you can translate that. You can substitute in the Fourier expansions of these and deduce the commutator for the wave modes, and those turn out to be A mu with. Hang on here. Let me just read it. That of lambda and p with A mu dagger mu dagger of lambda prime and q. And it's just what you'd expect, except that it causes problems. It turns out to be, and let me be sure here. Yeah, we get minus eta mu nu del 3 of P minus Q. The boy, if if you're the only people who show up for this, we can be very flexible about our time, at the very least.
Very true.
Yeah, although Guillermo did say he plans to come. Let's see, who was it? Now, Kevin, I talked to Kevin, he wants to come. So let's see, and who else?
I thought it was really just Lyle who wasn't.
Yeah, it was only Lyle who wasn't planning on coming. So I don't know where everybody else is. Let's see, who was the other person? Kevin, and who was working with you, Eli, on the final?
It was Guillermo.
Guillermo. Oh, Guillermo and Lyle, right. Oh, so Tyler.
Yeah,
Oh,
Tyler.
Yeah. Okay. So
I was just checking, and they are all in the officially listed as in this Canvas.
yeah, everybody who said they, were going to do it did reply when I opened up the Canvas site.
I know that Guillermo thought that maybe last week we were meeting on Monday, and I thought that kind of on the side too.
Oh,
maybe there was.
Oh, really? Yeah, I wasn't ready yet.
Yeah.
Sorry if there was confusion about that, but yeah, maybe I should send out emails to everybody and let them know, and let them know that there's a recording that they can catch up with. So what this does is introduce a weird sign. So we know that A and A dagger have an interpretation as creation and annihilation operators, but that happens because of this commutation relation. If we act on some kind of an eigenstate, then we get an eigenvalue for, well, let's say the energy. Then if we act with a dagger on that state, and then act with the Hamiltonian, the commutation relations allow us to work that through, and we see that we get a bigger energy. And so that's what makes a dagger a raising operator. That doesn't happen for the time-like one, right? Because eta has indefinite signature. When you have time here, it changes the sign in such a way that it's actually A that raises the energy and A dagger that lowers it. So it comes out exactly backwards. And that's bad because it means that you don't have a Hilbert space, right? If you take the usual definition of the vacuum, the set of states annihilated by the A hat, then what you find is that acting with A hat dagger, right, A0 dagger creates states of negative norm. And let me see if I can, yeah, I can just run through that one if I can put this silly cat down.
No.
She looks awfully comfortable.
Yeah.
No, you can't.
All right, I can't. So yeah, so let me see how this goes. The Rosalind, I hate to say this, but it's time. Come on, there you go. There you go. Go. All right, so here's basically how the argument goes. If we look at the norm of a state, so we have some P lambda here, and we're going to write that as if P lambda is created by A0. So let's let let's let the state P lambda be proportional to A0 dagger acting on the, oh, sorry, I kicked the cat, on the vacuum. So this is A of some lambda and some P acting on the vacuum state. So this is annihilated by A0. So now when we put a pair of these together, okay, we're going to get that normalization, and then we're going to integrate over an inner product. Why is that? This is missing a line, but this would be the dual of this. So here we have the vacuum, and then a hat 0 acting to the left on the vacuum, and then A0 dagger acting on the vacuum this way. And you write this using the commutator. So the commutator is now going to be, right, we can write this as A0 dagger A0 plus the commutator A0 dagger on the vacuum. And this is going to annihilate the vacuum. So that term goes away. But the commutator is now has the wrong sign. Let's see, 0, 0, 8, yeah, 8 of 0, 0 is positive, so we get a minus sign here. So this is going to be minus delta 3. And the crucial thing here is that that's negative. So we've introduced negative norm states, which can't possibly be physical if we want our usual interpretation of Hilbert space as giving us probabilities. You can't have negative probabilities. That would just be weird. So what we do, there's a formal reduction of all of this. In order to deal with this, what we can do is ask for the entire space of states. Now, first, what do we mean by the entire space of states? Let's go ahead and define the vacuum as the state annihilated by all of the A operators, all of the A mu at every lambda and every momentum annihilates the zero ket. And that defines some state. So we're going to build from that. And now we build states by acting with the A daggers. But what we're going to require is that the states, let me see which ones now. We want to deal with the states that are created by this spurious term. The ones we want to eliminate the negative norm states. The negative norm states are the ones that had an A0 dagger in them, and it turns out we can eliminate those if we look at d mu a mu as an operator. All right, that's going to be a sum of A terms and A dagger terms with various stuff here. All right, and what I want to do is define d mu a hat mu plus to be the terms that depend on A dagger, and d mu a mu minus to be the ones that depend on A. So the sum of these two gives us that operator divergence. And the condition that we want is that let me be sure I have these signs right. We want to restrict physical states to be those annihilated by this minus operator. So it's sort of amazing how this all works, actually. So if d mu a mu minus acting on any state, let's see, let's see, what do we want to put in here? How did I label it here? Yeah, we've got some K's and some lambdas, but there might be a whole bunch of these characterizing a physical state. But we want to consider the subspace of states where this operator annihilates the states. Any state annihilated by that operator is allowed in our physical space of states. If it's not annihilated by that, it's not part of our physical space. Now, it's not hard to show, and let me see if I can actually do it. All right, so the states that are annihilated by that operator. First off, notice that this is a weaker condition than the Lorentz gauge condition. We're not requiring this whole divergence field to vanish. We're saying that we're restricting the space of physical states. So this is something that happens way at the end of quantization, not way up at the beginning. And it allows more things to happen in between. And in particular, we get around the problem of this vanishing momentum and having to deal with the projections and particular gauges and such. Now, to actually specify which conditions satisfy this property, let's start with a general creation operator. And let me see how I've characterized this. Yeah, so I actually wrote a quite generic creation operator here. I called it S. And yeah, so if we act on the vacuum state with this, all right, so what is S? Well, I can take a superposition over momenta, E3Q over some normalization, I to the 3/2 to omega. And then sum over Fourier modes, I q dot x. And now I want to act with every allowed creation operator. And I'm going to organize them in this way. We can have polarization vectors that are along Q. And their corresponding A daggers. And then we can have things that are, how did I get these? Transverse, so just the spatial directions, QI, epsilon I, and those corresponding A daggers. And then we can have the actual transverse states, which I can take a linear combination of, remember our projection operator to the transverse states. A Kronecker minus KK projects orthogonally to K. And then those states acting on epsilon nu and their corresponding A daggers. And then, so, you know, that's sort of the, yeah, that includes the superposition of all the possible different creation operators for the different polarization vectors. And we can act with those and, you know, add up over all momenta, where your P mu nu is this projection operator minus K squared K mu K nu. This projects orthogonally to K. If I act on I let this act on K, I get K here. Then I get K squared there that cancels this and leaves a K, so K minus K is 0. You can always build a projection operator that way. So now, in order for this state to be annihilated, we need it to commute with S dagger. So we want these states to be annihilated by d mu a mu minus. And those acting on S should give 0. And we can do that if we write this as S dagger on d mu a mu minus acting on the vacuum plus the commutator d mu a minus with S dagger on the vacuum. This is an annihilation operator, or a superposition of annihilation operators, and so that's going to give 0 on the vacuum. So the condition we need is for this S to commute with this divergence of A minus. All right. So what does that give? Well, now we just run through the commutator of this operator with each of these. And right, because this is, let's see, d mu a mu is, it's a longitudinal null thing. Let me see how I ended up writing this. Yeah, in the Fourier transform, the d mu pulls down the wave vector k. And so what happens when you commute this is that you're going to end up with that k dotted into these various things. Well, that k dotted into the p is 0 immediately. So these transverse modes are fine. What happens with the longitudinal and null modes is that the null modes survive automatically. The longitudinal modes, when I say longitudinal here, I mean those excitations in the direction of propagation of the photon. Okay, so well, if you think classically, transverse wave, E and B are perpendicular to the direction of propagation. Those are transverse. The longitudinal direction is the direction of the three-dimensional wave vector, Ki. And then there's a null mode in the direction of the space-time wave vector K mu. K mu is a null vector. It has to point along the light cone. So those four directions are sufficient to characterize this. Now, what happens is that when we take the, let me work through the one of these that's actually most important. It's easy to see that if you whack this with a K, this is gonna go away. But let's look at least how one of these goes. If I look at the commutator d mu a mu minus with well, let's see, what did I call this? S1, just the first term up here. Okay, so what happens is you have this, you're gonna get a minus I, E3Q, all these normalizations like this. And then you have a sum over polarizations, double sum over lambda and lambda prime. You know, one of these can be lambda, one can be lambda prime. And then, let's see. Okay, whole bunch of stuff. I'm gonna need more space here. So we're interested in this one. So I'm substituting in the Fourier expansion for the vector potential. So then this is dot x. Then we have k mu epsilon mu of one of these at lambda, and then here q mu epsilon mu of lambda prime. We get both of those. And then we get the commutator of the A hat of lambda k with this a dagger of lambda prime and q. Okay, and then this is going to give us let's see, an eta lambda prime. It's going to give a delta of k minus q. That'll just let us do the integral. But the eta is going to combine these two polarizations. I better make those sums different. Yeah, okay. So here's what happens. This is delta of k minus q. And there's another factor. There's probably an I that comes into this somewhere. I may have lost an I in writing this down. There's probably an I here. But this commutator gives us that. And now using the sum over the polarizations, eta lambda prime with epsilon mu lambda epsilon nu lambda prime is going to give us an eta mu nu. So these polarization vectors get replaced by a metric that contracts k and q. And then the delta function makes k equal to q, and then that's the space-time square of a null vector. So this is all zero automatically because this metric with that k and that q together with this delta function give us a k squared. Did I say it too fast? You're good. Okay, great. All right, so that allows this mode along the null cone. This one, however, is not allowed because this inner product doesn't give you the full metric anymore. So this one does not work. And then this one does because k is orthogonal to p. So you get two of the three possibilities here. There are really two modes transverse, and you get the null case, but you do not get the transverse mode. So that allows us to characterize the states that are annihilated by this operator. They're anything generated by either this null part of the polarization or the totally transverse modes of the polarization. So now we can look at the norm of that space, and objects in that space actually have non-negative norm. So we've made progress. This actually succeeds in eliminating all of the negative norm states. Let's see, and I proved that a little further down in the notes. I'm on page 247, 248 here. So this has accomplished most of what we need. It's still not a Hilbert space, right? It's not a Hilbert space because there are still some zero norm states. We don't want, we want to have a positive definite norm. So we want a state to vanish if and only if its norm is zero. Now, this leaves us with the problem of characterizing these zero norm states. And what they are the ones, they're these null ones, right? They're these states. And it's for very much the same reason. If I create a state with this A dagger with the null polarization, let me call this, and I find the norm, I'm going to end up with a very similar integral here. And it's going to depend on k squared, and those are zero norm states. So what do we do with them? And now it turns out that you can do something really cool. It's you can show that they don't make any difference. All right, if I take any transverse mode created by this, and I add any amount of these null modes, and I look at the norm of such a state. Well, so let me be, so suppose that the null part is this, and I've got some transverse part here. So a general state is a superposition of some phi stuff created by these null creation operators plus some transverse stuff created by those. So those are the only kinds of states that are left. So they can all be written more or less this way. If I take the norm of such a state, so I want, you know, the norm of this, well, I'm going to get the norm of the t, and I'm going to get some cross-term type things. You know, I'm going to get like the real part of this, and then I'm going to get the norm of the phi part. Well, we already know the norm of the phi part is 0. But also, the inner product of one of these with any transverse state is 0, because these are in the Q mu direction, and this is orthogonal to that. So when you carry out this kind of a normalization of these states, you see that the transverse states are orthogonal to the null space. So this is 0 as well, which means that the norm of any t plus phi state, I'll just write it cryptically, is equal to the norm of the transverse part. We have an equivalence relationship here. So any two states that differ by any combination of these null modes will have the same norm. And so what we do is we quotient out by this equivalence relation. You both familiar with the idea of equivalence relation? Okay, good. So I'll just press on then. Having the norm of these states independent of phi, we now go on to any observable and look at the expectation values of any observables. And let me just run through that because it's just 3 lines. Look at what happens. I think I've got this right now. Let's see. Yeah, I fussed with this a bit to get it right. So, so let's let B be any observable. Ooh, isn't that a nice color? So let's look at eigenstates of B. So we've got some real eigenvalues here in a complete basis. And so now for any p and lambda and phi, right? So phi probably depends on p. If I look at the expectation values of B between any such pair of states, like this, all right, I can expand that. And let me see how I expand it. All right, so we sum or integrate over all these eigenstates, and I'm going to put in a complete basis. So we have p, lambda, phi p, and beta here. And then we pull out a beta, and we have a beta here, and k, lambda prime, phi k. And the point is that these are inner products of states in these equivalence classes. So these actually only depend on the transverse part. And so the result of this is independent of the phi parts, which shows that expectation values of any observables are going to be independent of those null modes. And so now there's no physical consequence to the null modes. And we've now, if you take a quotient by this equivalence relation, then we now have a space of states such that the norms are given by the norms of the transverse parts, and those are all positive definite. So in every equivalence class, we have the norms of all the states within the equivalence class are given by the norms of the transverse parts, which we know to be a Hilbert space from our previous constructions. So we've got a Hilbert space. This is, let's see, I think this is this the Gupta-Bloiler technique? I think yeah, Gupta-Bloiler. I should say that there is, there's a huge history spanning about 50 years of dealing with the quantization of electromagnetism and in general of gauge theories for internal symmetries. This includes like the weak interaction, the strong interaction. How do you quantize these theories when you have gauge invariance that only makes the problems that we see in electromagnetism worse? And there's a whole chain of things. So you can pick a gauge, yeah, all right, but now your results aren't gauge invariant, and not everything has a conjugate momentum, and you have, you can restrict things down, perhaps, in a non-abelian theory. It's not as easy. But what was gradually found is that this kind of introduction of spurious modes and a subsequent reduction afterward by some kind of condition on the space of states works really well. Another technique, more general, probably applicable to non-abelian gauge theories, is to introduce Fedayov-Popov ghosts, negative norm states that more or less cancel out the negative norm states that you don't want. The most sophisticated presentation of this seems to be the BRST quantization, where there's a systematic way to introduce the additional fields. Essentially, yeah, I want to look at this, and we'll go over it when we start talking about the strong and weak interactions. But it looks to me like what you're doing is introducing a certain restricted form of a supersymmetry. It's not the usual supersymmetry that you see in like superstring theory or supergravity theories, but you do introduce some anti-commuting variables, some new anti-commuting fields, fermionic fields, that are coupled to the bosonic fields. And the consistency condition of that sort of, I think it's fair to call it a supersymmetry because it mixes fields of different spin. The consequence is that there are certain constraints that hold in such theories, and those constraints are just the right thing to let you build a consistent Hilbert space out of this extended system that has these spurious modes. So we'll be talking about that. I want to read up on it more and see to what degree I can build a synthesis for you of how that all works. But that'll be fun to look at. So what we've done here is in the direction of that. We've introduced some spurious fields, the longitudinal and null modes, and we've arranged things in the end so that the space of states is nonetheless a Hilbert space, even though there are negative norms to some of the states we introduced. Okay, so what do we do next? Let's see. All right. Further work with the propagator. I'm just working my way through chapter 10 here. I assume you've read chapter 10 and that you're more or less familiar with these ideas. So what do we do? I'm looking again, at the propagator for the, now for the electromagnetic field. And in general, you get a condition where you have a projection operator that needs to annihilate a certain matrix. So you write your green function as a matrix valued Fourier transform. So the Fourier transform gives you a momentum dependent matrix. And you solve for that and you get equation, 10.5 here. I'll write it out for you. Let's see. Yeah, K squared. Yeah, this kind of calculation is kind of fun. Inverting matrices when the matrices only depend on a few things. This is a trick that's handy in relativistic kinds of calculations. So what you get when you take the Fourier transform is K squared times the Kronecker u alpha minus 1 minus 1 over psi times now Ku alpha. And then this acting on the matrix D alpha beta has to be minus I delta. We're contracting on alpha here, so what we get is a mu beta over there. So we find we have to write something like this, where I should tell you the ansatz here. What we're saying is that the green function is something like this, where there's a matrix valued object here in your Fourier transform. So yeah, so we're integrating e cubed k times e to the I k dot x minus y. Basically something like this for the Fourier transform with the normalization. What did I use? 2 pi to the 4th. But the same kind of Fourier transform we did for the Dirac equation, except now we just write this explicitly as a matrix operator in space-time, whereas the green function for the Dirac equation was a matrix equation in complex 4 space, spinor space. So now we have the problem of solving for this D given this operator. Well, okay, here's a useful trick just for calculational purposes. This will come up in other places. You would like to know, first off, is this thing invertible? And the telltale sign of some operator like this not being invertible is that it's a projection. So you can always square it and see if it comes back to itself. If it does, you're toast, right? It's not going to invert. But this doesn't, try it. And now there's another fun trick here. I gave it as an exercise. Did you guys do that exercise? Did you have time to look at that? Find the inverse to this thing? So you just construct something, right? So what's it going to be built out of? Well, you've only got deltas and k's in the problem. So it's going to be built out of deltas and k's. So you take some delta alpha beta, and you take some combination of k alpha, k beta, and you whack that operator with this operator and see what alpha and beta you have to choose to make it go away, or to make it 1. So we're going to let R be that and demand that R alpha mu on k squared delta u beta minus 1 over psi K mu, K beta should be, what do we need? We want delta alpha beta. That'll do it for us. So I'm going to put in R here. Alpha delta alpha mu plus beta K alpha K mu. So you just work this out and make this demand. So what do we get? We're going to get a Kronecker here. We have alpha K squared delta alpha beta. Then we have cross terms beta K squared. This is going to be a K alpha K beta. Here's the beauty of the thing is that's all you can get, deltas and K alpha K beta things. So you just make all the K alpha K beta stuff go away. Then there's this cross term minus alpha 1 minus 1 over psi. Then delta alpha mu makes this a K alpha K beta. And then these two terms give minus beta 1 minus 1 over psi. And then you get a K squared, K alpha K beta. And all of that you require to be equal to delta alpha beta. Okay, so let me make space. But you see, unless this thing is a projection, this will work. We need alpha equal to 1 over K squared. Then what else do we need? All three of these terms are proportional to K alpha K beta. And so what we need is beta K squared, coefficient here, minus alpha 1 minus 1 over psi here, minus beta 1 minus 1 over psi K squared equals 0. And okay, I've got alpha is 1 over K squared. Now I can solve for beta. And what does it turn out to be? Yeah, so I claim proof left to reader, unless you want me to do it. 1 minus psi 1 over K squared. So there are values of alpha and beta that work. So the propagator for this generalized, well, it's a vector field theory, right? It's not Maxwell theory until we restrict the space of states. But it is a, it's some sort of a vector field theory. And all right, so exercise proved that these are right. Well, there's just another step to solve for beta. But now we have a solution for d alpha beta, right? So we're going to whack both. So this operator on d gives delta. So if I whack both sides of the equation with this operator, this just gives a Kronecker. So I've solved for d on this side. And over here, I'm going to have this operator, the inverse. So what that shows is that I can write d alpha beta as this operator. Alpha is 1 over K squared. That's right, eta alpha beta here. I'm going to lower an index here. And then beta is 1 minus psi 1 over K squared. And then K alpha K beta. And then, well, this is a function of K, but this is our propagator for this vector field. Right? Did you see how that worked? We had this operator on D equals delta. We hit both sides of the equation with this operator, and because this is inverse to that operator, we just get D on the left, and we just get this operator on the right. Good, nice nodding heads, that's great. So what do we do here? Well, the simplest thing to do is pick a cool value for psi. Like if this is your propagator, what value for psi is going to make this simple? Here's a hint. 1, right? You choose 1, that term's gone. And your propagator is just 1 over k squared times the metric. And that's the propagator that we'll use in our QED calculations. So the photon propagator then is this very simple, just 1 over k squared, which of course diverges in the asymptotic space, but it's going to be annihilated by those prefactors on our matrix element, just the way that the Klein-Gordon operator canceled the poles in the propagators for the outlying limbs, the external limbs. Okay? I know, you feel obligated to shake your head. Oh, yeah, I got that. But, ask questions, okay? If something's fuzzy here, just jump in with it. So we end up with the propagator is, let's see, minus I eta alpha beta over k squared. So that's the form that our propagator takes when we keep track of all the i's and stuff. And then we can offset that pole if we wanted the space-time version of it, but we don't really use that for the path integrals. So we don't need to worry about it. Okay, so how are you holding up? Need to get up and stretch or anything, or shall we keep rolling? Run around the room?
I think I'm good for a little bit, probably.
Okay, good, good. Yeah, all right. So the next is the interaction term. All right, it's, yeah, we're still gonna act like this is the gauge theory. So we wrote down the gauged Dirac action, and it turns out to be just the free Dirac action plus the free Maxwell action plus just one cross term. So the gauged action was psi bar I d slash minus m psi, but we made this the U1 covariant derivative, which added a term i.e. psi bar a slash psi. So this is an interaction term that is going to tell us how photons and fermions interact, how, say, electrons. And then we have the free Maxwell action, which, however, we have mucked with to add minus 1 over 2 psi. Psi is 1, d mu, a mu squared. So we take this as our action, and we know that on our Hilbert space, the effect of this is the same as the effect of the original Maxwell action, the gauged action. The thing that we're really interested in here is the interaction Hamiltonian, this minus IE psi bar a slash psi term. This is what's going to give the interesting bit to our Feynman diagrams, right? This is the term that is something other than free fields. So here, these describe some free vector field. This describes a free Dirac field. We've quantized those. We know what their states are. And we're going to take those as the asymptotic states. But now there's a term that couples those to one another. And well, what that means is that we now introduce a picture for this kind of thing. Well, the basic picture looks like this, where this is your photon field, and this is psi bar, and psi. So we have some sort of picture like this, where we have a vertex that depends on this term in the Hamiltonian. Well, that vertex has a strength minus IE times the gamma matrix, right? This A slash is a gamma mu A mu. So it's this that combines the three terms and gives us a vertex like this. And as we saw with the scalar field, the technique, the perturbative technique, expanding the interaction part of this in an exponential series for just that interaction term tells us that term by term, we can calculate matrix elements like this by writing all these possible diagrams and carrying out the various momentum integrations that are indicated. So we know what all these fields do, right? Psi can be expanded in terms of U and V, the four different basis spinors. And then we have creation and annihilation operators for particles and antiparticles. A annihilates the particle, B dagger creates an antiparticle, and then vice versa for psi bar. Notice we have one of each, psi and psi bar in this. And if we apply Wick's theorem to this, all right, so now we got to think, well, what was Wick's theorem? Well, at first order, we're going to have, let's see, what does Wick's theorem do? We end up with products of propagators. And what those correspond to are diagrams like this. There are actually 8 different processes that could be described here. So we could have a photon come in and pair produce. So we get an E plus and an E minus here. And let's see, that goes backwards in time and that forwards. Or we could have just depending on what's in the initial and final states, we could have a photon in the final state and sort of an electron emitting a photon this way. Or let's see, what else could we have? We could flip that upside down so these come together and give us a final state like that. Let me see. We can do this with E plus or E minus. So that's actually 2 different things. Let me see what else. We can have an annihilation where E plus E minus come together. So here's a pair creation. Here's annihilation into a photon. And let's see, there ought to be, there are 2 more. So you could have things going this way, or you could have things vanishing that way. Those are pretty weird. And if you look at any of these diagrams, every single one of these violates conservation of momentum. So none of those happen. And it's kind of fun to run through those. It's pretty quick. These obviously do, because you have no momentum in the final state and some in the initial. So these 2, no way those conserve momentum. Now for annihilation or pair production, the argument is quite simple. What we do is look at this in the center of mass frame, right? So in the center of mass frame, the momentum of the positron is going to be some gamma CV. So then the momentum of the electron is going to be the same gamma, but C minus V. And so the total momentum if we add those together in the initial state, is twice gamma c0. And that cannot be the momentum of this photon because that's not a null vector. And you're done, right? No photon can have that as a form momentum, and so the process is not possible as a real process. That leaves us with these two, and let's just run through it. It's just a couple of steps, but it illustrates the kind of facility I want you to have with special relativity for vectors and all that kind of stuff. So what happens here? We've got in the initial state, we've got a form momentum. So the initial electron, let's say the initial form momentum is some for velocity. Well, you know, what inertial frame do we want to do this in? Well, let's take it at rest. That's easy. Or better yet, let's take the final one at rest. So I can go to an inertial frame where the final electron is at rest. So the final electron momentum is just going to be, there's an M here, sorry. It's just going to be MC0. And the photon momentum is going to be, well, omega and K, where omega squared equals K squared. So it's got to be a null vector. So if you just write out what that does, we have pi mu has to be p final mu plus k mu. And the first simple thing to do is to square that. So if I square the initial form momentum, that's just m squared, right? Because the form momentum squared is the mass squared. And on the right side of the diagram, we square this. Okay, this squared gives us an m squared. Then we get twice p dot k. Well, this is why it's handy to take this one at rest, because the Lorentz inner product of these is going to be mc h bar omega. And then we have k squared, which is 0. Now, the masses cancel, and we have to have 2 mc h bar omega equals 0, and that only happens if the electron is massless or the photon is frequencyless, neither of which is the case. So we can't do this. And all 8 of those diagrams violate conservation of momentum. So now we're immediately looking at second order diagrams, and we write the Fireman rules for QED, which you've applied, so you remember these. Let's record them for posterity. What do we have? We've got the propagators. So internal lines get a propagator.
Keep on going. I just gotta grab my door real quick.
Oh, sure. Let's see. So, yeah, the one thing we haven't established yet, and it's the reason for that calculation I skipped. You know, working through the cancellations that occur between the propagator and those other parts of the external lines. Okay, we do not get complete cancellation yet. Let's just hold off till Eli gets back. Oh, sure. Here comes Eli. Whoa, is that food? That looks like, oh man. Can I have some? That looks like food.
It's Hawaiian food, yeah.
Oh, man. Hawaiian food. Oh, where'd you get that?
Mo Bettas is what it's called.
Yes. Oh, we should try that.
They're good.
Yeah. Meg spent half her life in Hawaii. So.
Oh, that's awesome.
Yeah, we probably have eggs and rice 2-3 times a week. Yeah. So, okay. Yeah, I was just saying to Alex that the one thing that's really different in these Feynman rules is how you treat the external lines. Now, I skipped that calculation. Getting the factors in that matrix element that will cancel the poles in the propagator for the external lines. That cancellation still happens, right? You still get like a k squared minus m squared that cancels the 1 over k squared minus m squared in the denominator of the Dirac propagator. But the polarizations and the basis vectors do not cancel. They're still there. And that's the second reason for running carefully through that calculation. You do not get a cancellation of those. So for external lines in a diagram, now suppose we have, maybe some second order diagram like this. And so we've got an electron and maybe we've got a positron going backward like this. And a photon here. Well, here we're going to put a photon propagator minus I eta alpha beta over k squared. At these vertices, for a positron, we end up with minus I e gamma alpha, or let's call it gamma beta. Over here, you have to multiply this by the charge. The charge is negative here, so you get a plus I e gamma alpha. And notice you match these indices to the ones on that propagator. Then for the external lines, we still need the basis spinors out here. So this is going to be a particle in, so we're going to have a U of P in some polarization. Here we have a positron out, so we're going to have a V of well, let's see, let's call this a P1 and a P2 maybe, and some other lambda. And then that's a V bar. Then here we have a V of, I'll call it P3 and lambda double prime. And here we're going to have a U bar of P4 and lambda with way too many primes on it. Something like this. So we have to label the vectors associated with the outgoing states. For the spinors, it's the basis spinors. For a photon, it's going to be either the polarization or the conjugate of the polarization. So then we have a vertex contribution minus IE gamma alpha, and then N is the charge of the species, where an electron will have a negative charge, and so it comes in with a positive sign. The diagrams you read following the fermion lines backwards. So you start at the far future for an electron or the far past for a positron, and read backward, writing down everything you see along the way. So for example, here, I'm going to follow the positron line backwards, so I'm going to write a V bar of P2 and lambda prime. Then I'm going to have the vertex operator E gamma beta. And then I get up to V of P3 and lambda triple prime. And this all gets multiplied by a propagator minus I eta alpha beta over k squared. And in this case, there's not a direct coupling between this and this line. This line is going to give me a U bar of P4 and a lambda triple prime, and an IE gamma alpha, and a U of P lambda. Now, notice what has happened here. Everything is contracted. Okay, I've got an alpha up here. I've got alpha and beta down here. I've got a beta up over here, right? That makes a Lorentz invariant quantity. All my Lorentz indices are properly summed. Now, spinor indices, they are too. If we have something like a U bar gamma alpha U, right? We know U bar has a down index. Gamma alpha is a transformation matrix. It's got mixed indices, and U has an up index. So this kind of a sandwich, a barred spinor field, a gamma matrix, and an ordinary spinor field makes a scalar in the complex space. These are like currents, right? That has the form of another current for the spinor field. And the same thing happens over here. We've got a V bar gamma V. That's a scalar. So the matrix element you write has to be a scalar in both spaces. It has to be a scalar in the spinor space. It has to be a scalar in space-time. So that's a check on whether you've written the right thing or not. So let's see. So given that, do go back and check that calculation of to see that you need the polarization or the basis spinors on the external lines. Okay, now, so depending on what's exchanged, we could have a diagram where we have a particle come in, and the particle exchange could be a fermion, and then this could go out, and you could have a photon coming in, photon going out like this. Well, this is the Compton calculation that you've worked through. And homework, I don't know if, I know, Alex, you started this, but redo the Compton. Okay, two things. First, I've posted the ultra-relativistic Compton solution online. And Alex was the one to notice that the cross term is 0, right? In the ultra-relativistic case, I had come out with S plus T plus U, but if you're neglecting masses, that's 0. And you know, depending on how you organize the terms, you may or may not notice that. But I did know there was an identity, S plus T plus U, but I didn't double check that, oh, look, that's 0. But anyway, compare your Compton results to what I've posted on the QFT website to see that you did get it right. If you didn't get it right, fix it. You know, find you know, grade yourself, right? You know, I worked it through. I tried to show you tricks that shorten things and you know, make it as concise as possible. You know, something that amazes me with these quantum field theory problems is how much cancellation there is. I mean, you do these pages and pages of reduction of products of gamma matrices, right? And you find it reduces to 3 terms or something. You know, everything else is just cancel out. Like, there's got to be an easier way to do this, right? And I haven't spotted what it is. Maybe one of you will be the one to figure out, hey, you know, this is just longhand for chi, and be able to write the answer. No, I don't see a way to do that. These are complicated enough, and you know, the answers are quite non-trivial. So if you'll recall for the Compton case, the second problem, after you check your ultra-relativistic Compton solution, now do it again with the masses. And I know, yeah, some of you may have started this already. I posted this on the website, but the Yeah, it's tricky. There are a lot of terms, a lot of cancellations. You get sort of every possible dot product of the various momenta on the cross term at least. But if you recall back when we were talking about the Compton effect, one of the wags in the class in chat wrote 1 minus cos theta. Well, yeah, non-relativistically. And you still see 1 minus cos theta in about, I don't know, 3 or 4 places in the solution. But the actual solution for all masses is much more complicated. That is only a classical approximation to something that is much more sensitively dependent upon the angles than just the 1 minus cos theta that we've done in classical mechanics or something, or where do you do Compton? It's a simple special relativity problem, right? To balance the momentum and, calculate the energy, and, that comes out, and that's still in there. That conservation of energy is still there. But the differential cross section depends on that factor in several different ways. So to see the details of that, you've got to go through this long thing. So go through the long thing. Let's see. Do I need to review these rules anymore? Let me scan through them. We're going to integrate over each undetermined momentum. So in the problems we're doing, we don't have any undetermined momenta. Then we end up putting in 2 pi to the 4th times a Dirac delta, giving conservation of overall momentum. So in the case where we've got 2 particles in and 2 particles out, you write the differential cross section. Now the total cross section, you're going to integrate over all final states of the particle, right? To find the total probability of scattering, you integrate over all the scattered particles. For a differential cross section, if you have 2 particles in and 2 particles out, you integrate over all the final states of one of the particles. That takes care of your Dirac delta function. You leave the other angular integrals undetermined, and that's what makes the differential cross section differential. So for in different elements of solid angle, you're making a prediction of the number of particles that are going to go into that solid angle. We do differential cross sections in the next chapter, and I'll talk about that in detail. But
that was step 4, like integrate with the undetermined momenta. Is that?
Yeah. Well,
that idea?
Yeah. There are other undetermined momenta, because when we go to higher order, we're going to have some loops, and they're going to cause problems. So what we're doing so far are diagrams with 2 vertices, and they're fairly simple. But if you go to next higher order, you could get a photon doing this, right? Or 2 photons exchanged. And now you have a closed loop here, and nothing controls the amount of momentum that goes around that loop. As long as whatever goes down here comes back up over here, you've conserved the momentum at the vertices. And that leads to some divergent integrals. And we need a systematic way of dealing with those divergent integrals. So we're going to discuss loops as you continue doing some straightforward scattering or pair production problems. I'm going to want you to do, say, muon production. So if you send in, say, an electron and a positron in such a way that they annihilate, that can produce a photon. Well, if you've got an energetic photon around, it can pair produce anything. And at the next energy level, what it's going to produce is a mu plus mu minus pair, a muon and an anti-muon. And the differential cross section for that we can look at. And it's probably going to vanish unless the energy of these is sufficient to produce those muons. There's another production. Let's see now, how would you do this one? Yeah, electron-positron collisions where, there's another thing you could produce here. You could produce a Z0 particle. So this could be a photon, but this could also be a Z0. And if you have at least 91 GeV available in your electron-positron collision, you're going to start seeing Z0s. In fact, if you let the center of mass energy of your collision sit right at 91 GeV, you're going to get a resonance, right? You're going to get a very strong production of Z0 particles. And, this is the way they produced them in the first place. And then any energy higher, some of the interaction is going to be Z0. This happens in hydrogen. Okay, electron and the proton. All right, they're exchanging virtual photons. Every now and then, with a probability that's probably 10 to the minus fourth, 10 to the minus fifth times smaller, they're going to exchange the Z0 particle. And that gives a very small correction to the energy levels in hydrogen, which we can measure extremely accurately now. And we can see the effect of the Z0 exchanges. I'm not sure what decimal place it shows up in, but it's there. So, these are very real, measurable effects that tell us a whole lot about what can and can't happen. Let's see. Let's see. 6 is okay. Labeling the external lines. It's handy to draw the directions on the fermion lines. The fermion lines are always continuous. You don't have a break in a fermion line, and you can track them against the arrows to write the matrix element. So the positrons go backward. So if you had a positron in and a positron out here, you'd have the arrows going the other direction, and that's another interaction. Then the procedure is, as you know, to compute the matrix element corresponding to each diagram at a given order. So we've shown that none of the first order diagrams conserve momentum. So we're starting with second order. So we have diagrams like these for electrons and photons. And so order by order, we can get corrections to the total cross section. But then you calculate a matrix element such as this for each of the different possible diagrams. You add them all together and then you square them. And this is a remarkable thing, even though the ultra relativistic Compton case gives 0. If you put the masses in, that cross term does not vanish. It depends on constants times m squared or m to the fourth, and they stay. And, they're not too horribly bad. But the fact that they're there tells you something about the nature of this quantum thing we're describing. This is a lot like, I think I mentioned this last semester, a photon in a double slit experiment. All right, so you send a pulsed laser toward a narrow double slit, and you get an interference pattern. Now you choke down the intensity of the laser until on average there's like 10 or 20% of a photon in the system at any given time. So basically if there's anything, it's one photon. You still, collecting what happens, see an interference pattern. So the photon interferes with itself, right? These electrons and positrons, they they're interfering with themselves. So it's really the same thing happening here, that, you know, what's going on is really more mysterious than any one Feynman diagram. That one Feynman diagram is not what's happening. What's happening is some superposition that includes an interference between, you know, this diagram and that diagram, or, well, you know, which, yeah, if this is an E plus E minus coming off here, that diagram and interference between them tells us what happens at lowest order. So that's weird, right? That's, you know, spooky action at a distance, maybe, or spooky action anyway. Yeah, Alex, question.
I even had a question on that. In the ultra relativistic limit, I was wondering, are those the zig and the zag states then? Like, is the T channel like the zig and the others the zag in the ultra?
The zig and the zag.
Because they look orthogonal, but and they don't interfere.
I mean, the cross term vanishes, yes. Yeah. So yeah.
And one's time-like.
Is it these two diagrams I think we're talking about? So if we have E plus E minus in, E plus E minus out, these two things or their interference can happen. And the interference only happens to the degree that we keep track of the masses. So you'll see that being non-zero when you do that calculation. But let's see, you want to call one of these zig and one zag?
Yeah, I was just, because one's a space channel and one's a time channel. And so I just wondered if maybe the early theorists were trying to look at it that way, but then they found that there was that interference term with mass that they couldn't say, oh, well, zig and zag.
Yeah, absolutely. People do talk about the time-like channel or the space-like channel. And, you know, here the photon is time-like, here it's space-like, right? And it's definitely off shell, it's not null, right? It's space-like or time-like. The momentum transfer along these lines is going to be that momentum is going to be a time-like vector or a space-like vector, and that's Lorentz invariant. So you can talk about that. The Mandelstam variables, which I guess I haven't talked about, but I wrote down. Let me see if have we gone through enough of the Feynman rules? Oh no, I want to talk about the sum over spins and polarizations a bit. But the Mandelstam variables definitely are time-like or space-like channels, right? They correspond to the type of momentum exchange. They're Lorentz invariant things, but they're Lorentz invariant things that depend on a pair, a sum or difference of four momenta, but they're magnitudes of those sums or differences. So they're Lorentz invariant quantities, and space-like and time-like are meaningful there. But yeah, before I define those, let's finish these Fireman rules. So if you measure the spins and or polarizations of the incoming or outgoing particles, then you keep track of that through the whole calculation. And you assign definite polarizations to what goes in and what comes out. And that affects the matrix elements that you write down. When you're writing here, for example, if you know that the incoming electron is in a spin-up state, you could arrange that, right? You run it through a Stern-Gerlach thing and select the spin-up electrons and send them into the scattering. So what you would do is, right, you use those projection operators we developed, and you use just the spin-up basis spinner here. Then when you use the completeness relation to write products, outer products of U and U bar in terms of gamma matrices, you include the appropriate projection operators. And we'll come to that later when we're work through one of these carefully. Maybe I'll do Baba scattering in detail and we can talk through those steps. But if you do not measure spins or polarizations, then what comes into the experiment is the average of all the spins or the average of all the polarizations. So you take half the sum over all of the spins, for example. And if you've got two particles coming in, then you've got a quarter of the sum over the spins of both particles. Then for the scattered particles, you're going to measure everything that comes out, so you sum over all the final spins. So for the matrix elements we're doing, we're going to need to calculate the square of this or the product of this times the conjugate of that and so on. And then we're going to sum those matrix elements squared over all final spins. We're going to average over initial spins, or we're going to average over initial polarizations and sum over final polarizations. And that lets us use some simple identities to replace those vectors with a trace of gamma matrices. Okay, Mandelstam variables. Yeah, these are sort of easy, except that for certain diagrams, they're ambiguous. So I'm finding it helps to actually just define them for a given problem and draw the picture of the problem in a way that makes it consistent across all your diagrams. So for, let's see. Yeah, the kind of problem you run into is, okay, so if you have two particles coming into an interaction, you have some interaction and you have two particles going out, then let's call this P1 and K1 and P2 and K2, for example. Then we define S to be the squared norm of P1 plus K1. And notice these are momenta squared. So for example, here the total momentum in this photon is P1 plus K1. You know, it's going to be the sum. That's the S channel. That's the time-like channel. Okay, then if we have something like this, the momentum exchanged here is going to be P2 minus P1 is what's going to be the energy in this photon. And that's the T channel, the square of that. And then U, you see the U in a diagram like this, where now we've got K2 up here and P1 down there. So we have, so what's in this channel, let's see, is, wait a minute. Am I doing this right? How did I define them here? P1, yeah, so yeah, P2, wait a minute. P1 minus, I'm writing these backwards. Let's see, so you start with P1 coming in, and then this channel loses this much, so the channel has P1 minus P2. Or if you're looking at a diagram that goes the other way, where this photon comes out there and this particle comes out here, sometimes you can interchange those, right? And be seeing that process. If you just see a photon and an electron, you know, which do you see where? Well, then that's a U exchange, and that's going to be P1 minus K2. If I've done this right, this is, yeah, a 1 minus a 2 and a 1 minus a 2, but it's the other 2 here. Okay, so you have to be a little careful, because in this one, you know, you can flip around this and it doesn't do anything. You know, that photon doesn't care which one comes out where. Or if you're doing, if you're doing electron scattering, you can actually interchange those. So what you call P1 and P2, or P2 and K2, you know, how do you know if these are interchanged? So you need to define your terms and draw your diagrams consistently, so that what you mean by K2 in this diagram is the same thing you mean by K2 in this diagram. So if P2 is the final electron momentum, you want to label this one P2. And it helps if you draw your pictures the other way here, like this. Even though you can put that either way, if your P2 is here, you want to put P2 there as well. And now you've defined your variables consistently. So double check that. Draw all your diagrams. Make sure your Mandelstam variables are consistently defined across diagrams.
Professor, do these variables like kind of only work for 2 in, 2 out, or are there generalizations to n in, p out, or whatever?
You know, 2 in, 2 out is you can. I mean, sure, you can write generalizations. You can define more variables, right? Essentially, given conservation and momentum, you can write the dot product of any pair of momenta here in terms of these Mandelstam variables. So for a 2 on 2, you're good, together with conservation of momentum. In fact, that gives you a relationship between these, as we've seen. S plus T plus U for these diagrams is m squared. But you can multiply it out and check it, right? You can explicitly see what relationship there is between these. If you have more particles in or out, you have more momenta, so you have more dot products, so you'll probably want to define some new variables, but you can. You can certainly write everything in terms of you know, some number of squared momentum variables of the same sort. So, you know, this might be a good spot to pause, unless you're feeling really revved and want to try and do a problem. You know, I've come to my example of electron-positron scattering. That's called Baba scattering. And, you know, a worked example here. I think the main thing that I think we should do at this point is to all compute some of these things. So first, do the Compton with mass. And I'm happy to compare notes with you. I'm not sure if I've quite got it yet. I might have it. I might have gotten it this morning. I spent the morning working on that one, and it's looking more and more consistent. The more times you work through these, the more regular you can be with the arrangement of terms and how you proceed through the various simplifications. So you get it's a whole different kind of perturbation theory. You home in on the right result for the calculations. There's so many things to keep track of with these that it is very easy to slip up and lose a factor of 2 or a sign or something like that, and end up with, you know, weird numbers like, you know, not quite small primes, like 7 or something like that, which seems to be occurring in this case. But, you know, we'll see if that survives into the ultimate prediction. I would worry if I got a coefficient of pi, but you can get some things that aren't exactly powers of 2, or, you know, some, small powers of 2 and 3 or something like that. You know, that can happen. So go compute. All right, try the Compton scattering with the masses, and you know, feel free to you know, come ask questions if you have them, if you run into any problems in carrying that out, or you just want to check if you're getting something similar to what I get. So the first of us to get to the right answer wins. And it may not be me. As I say, I think I'm pretty close to having the right answer for this one. But let's do a few of these. We can do that muon production. We can do Baba scattering with the masses. We can do, let's see, what's Mott scattering? I forget what Mott scattering is. That's another one of this sort that can be done. Hang on, let me see what Mott is. Let's see, Mott scattering. Oh, Coulomb scattering. It's the quantum field theory version of Coulomb or Rutherford scattering. There's a trick to that. You can't, Rutherford scattering doesn't quite exist, right? You have a charged nucleus and you're careening say an electron or a proton off it. And you get this 1 over sine theta over 2 to the 4th power as the leading coefficient. There are corrections to that. And the only trick is you need to handle the recoil momentum of that nucleus. And I have to remind myself how that's done. But yeah, we should talk about that because it's nice to see that, yes, you get out the familiar old classical Rutherford scattering result, but there are quantum field theory corrections to it. So let's look at some of these. For lectures, we can certainly do some examples. I've found it helpful if you've got a trace of a whole bunch of so you've got P1 slash plus M, say, and gamma alpha P2 slash plus M, gamma beta P3 slash plus M, gamma U, and more stuff. Okay, you're going to have some propagators out here that are going to give you maybe an eta alpha mu. Right, so you're going to want to reduce those two matrices, but you can't, right? Well, it's easy to show that gamma alpha P slash gamma beta eta alpha beta is what? Well, you permute these two, right? So you have eta alpha beta gamma alpha, then you get two terms here. You're going to get a minus sign if you flip them, or if they're the same gamma, you're going to get twice an eta, which is going to put that beta on that P, so you get a P beta. So you get something like this, and then you can work this alpha back to the other side. And let's see, so you've got eta alpha beta. Let's see, what is it we want to do here? Oh, no, we're already there. Eta alpha beta on the product of two gammas is 4. So we're going to get minus 4 P slash. But then this eta, that gamma, and that P gives a plus 2 P slash. So the net result is minus 2 P slash. So if you ever see this in your calculation, you can replace it by minus 2 slash, and you've gotten rid of 2 gammas. Now, you can carry that trick further. If you have something like this, well, it's pretty much a no-brainer that if you've got a P slash plus M between 2 gammas with an eta, okay, this P slash gives minus 2 P slash, but the M is just an M, so you're going to get the 4M. So if you have two gammas surrounding a p slash plus m, it's minus 2p slash plus 4m. All right, carry it a step further. Well, now, what about something like this? You really would like that gamma interchanged with that gamma. So now you have this thing, right? If you've got an eta alpha mu here, you like to interchange those two. Well, what you can do is you can write this product, gamma mu. You can write that, you can show that this is minus gamma mu p 3 slash plus m gamma beta plus a bunch of stuff. And that stuff has two fewer gamma matrices in it. So work that out. Now you can substitute all of this for these guys. And this term, now you can use this eta to on this gamma and that gamma and this p slash plus m. So you can build your own set of simplified rules. Okay, and if you have a few of those on hand, it'll shorten these calculations a bit. So go for it. Do you want to see that worked out? Or yeah, it's not hard to do this yourself. Just commute gammas through. You can always write a p slashes p alpha gamma alpha, and that's just a function. You can put that anywhere. So use your fundamental Clifford algebra anti-commutator to rearrange the gammas the way you want them and simplify these things. I think one other problem I gave, and then maybe we'll wrap up for today. I said that 15 minutes ago, didn't I? All right, hang in there. One other thing to try, there's photon scattering, right? And why don't you write this down? Now, this is interesting because it demonstrates, why people do these things on supercomputers. Suppose I have two photons. Well, in Maxwell theory, they just pass through, nothing happens. But at fourth order, this guy can pair produce backwards, E plus, and then that guy can, let's see, which way is this? Well, electron, I don't know what that is, but yeah, if that's, these should alternate. Let's see, let's make this an E plus point that way and make these guys go. That's wrong. Let's see. So that's like pair production. I might have my arrows wrong, but the point is there is a diagram like this where two photons come in, both pair produce, and you get mutual annihilations of the pairs, and two photons go out, and that's a non-trivial scatter. So electromagnetism becomes a nonlinear theory in quantum field theory in QED. Now, what I'd like you to do is to write the matrix element for that diagram. And what you're going to see is, okay, each vertex has a gamma matrix. Each propagator has a gamma matrix. That's 1, 2, 3, 4, 5, 6, 7, 8. You're going to square the matrix element, 16 gamma matrices. How many terms does a trace of 16 gamma matrices have? Or what is 15 double factorial, right? So, all right, so, that I'm not asking you to reduce a trace of 16 gamma matrices. If you're feeling really adventurous, you could try it, but write it down and stare at it long enough to convince yourself that you're glad someone somewhere has written computer software that will take traces of products of gamma matrices and calculate even fourth, fifth, possibly sixth order diagrams if you give a supercomputer enough time. does take quite a bit of time. So plenty of things to work on. So first, check your ultra relativistic Compton result against mine. Let me know where I made mistakes. 2, do the Compton scattering with mass. 3, rate the photon-photon scattering. That's plenty to keep you busy until our next meeting, I think. Meanwhile, don't hesitate to get in touch. We can Zoom, we can exchange emails and check one another's calculations, because these are long and hard to get exactly right. So mutually, we can all figure this out. Feel free to work together, compare notes. And let's see, what else? Other than that, read chapter 10. Right, let's see, where did, I lost my notes here, but where did they go? Oh, there it is. Yeah, chapter 10, I think ends with the Baba scattering. Oh no, I've stuck in the ultra relativistic Klein-Nishina. Klein-Nishina is the Compton scattering problem we've been doing. So I have, I think, a pretty sensible version. Oh, this goes on and on quite a long time. But yeah, so read chapter 10. And yeah, then we'll do more of this next week. So Monday, 2 o'clock, unless we negotiate out some other time, but I think this should work for, well, at least the 3 of us. And Guillermo says he can make it too. We'll have to, yeah, if you see Kevin or Tyler, razz them a little and encourage them to check the recording and join us next week. So, any questions? Are we good?
No, not right now.
Okay. Yeah.
I need to think on it before I can have any sensible questions.
Yeah, absolutely. So, reread chapter 10 and, compute. Try these trace things and see how it goes, and then be in touch.
Sounds good.
All right. See you guys.
Thanks, Professor.
You bet.
Have a nice day.
You too. See ya.
Bye-bye.
Bye.